Hi everyone, Mr. Lee here. In this video, I want to go over the graphical nature of the motion equations. Let's begin. So to start off, let's go over the equations that we know for velocity and for acceleration. So we know that velocity is equal to the change in position, aka the displacement, over the change in time. We also know that acceleration is equal to the change in velocity divided by the change in time. Now, I'm going to do something special here. I'm going to rearrange the variables here so that we have everything in the numerator. So that gives me, I'm going to multiply both sides by delta t. So I get the displacement is equal to velocity times time, or the change in time. And when I multiply here, I get delta v, or the change in velocity, is equal to the acceleration times the change in time. And you'll see why I do that in a little bit. Okay, so with these equations stated, let's do a graph. So if I have a position versus time graph where my units are seconds and in meters, and let's say you're given a function like so, all right? And let's do something like this. Boom. Okay, so we're given a function like so, and it's split up into three parts: 1, 2, and 3. Okay, 1, 2, and 3. And the question will ask you, what is the velocity of the object during portion 1? Okay, so if you're given a problem like that, the question is asking, what is the velocity? But you're given a position versus time graph. The best way to approach this is to actually take a look at the velocity equation. So we see that velocity is the change in position over the change in time. Now here what we have is a division, okay? And the division is the change in the y-axis over the change in the x-axis. So whenever you are dividing your y by your x-axis, what you're looking for is slope. So in order to find the velocity of portion 1, all you got to do is find the slope of that line. Okay? And so let's take a look at a different graph where we can use the same strategy. So let's say that we are given a velocity versus time graph, okay? And we're given a velocity versus time graph that looks something like this, okay? Where this is section 1, we can say this is section 2, this is section 3, and we can say that this is section 4, all right? So we have 4 different sections here. All right, and so if the question is asking you, what is the acceleration during section 1. So we're given a velocity versus time graph, okay, so those are your known variables, and they want you to find the acceleration. So if I take a look at my equation for acceleration up here, I see that my acceleration equation has delta v divided by delta t. So once again, it's division. And not only that, but I'm dividing by, now this is important, my y-axis by my x-axis. Therefore, my slope is my acceleration. Getting the hang of it? Okay, so we just covered how we can use these top 2 equations given different graphs and what we can determine it from there. Now, if you ever forget your equations and you just don't know, right? So let's say you're just given a position versus time graph and you don't know what the slope represents. So all you have to remember is this. Slope is, okay, delta y over delta x, the change in the y over the change in x, and use the units because any good graph will always give you the units, and that's why you should always include the units as well because they're clues. They give us an insight into what we want. So our units for the y-axis is meters. The units for the x-axis is seconds. So if we take a look there, we get meters per second, which are the units for velocity. Therefore, the slope for a position versus time graph gives us velocity. Now let's see if that strategy holds true for a velocity versus time graph. Okay, so you don't know what the slope represents for a velocity time graph, but you do know that slope is rise over run, and our rise units are meters per second. Our run units are seconds, so meters per second gives us meters per second squared, which are the units for acceleration. Okay, so that's a nice little trick that you can use just in case you forget what the different graphs and have for the slope. Now let's try the bottom row, these 2 equations. Okay, so if we take a look here, we have velocity and time. So I want to focus on that one first. So let's say we are given a velocity time equation. So it's a velocity time graph, and let's say that we are given, I'm going to do something very unique for us here. I'm going to do like that. Oops, that should be a straight line, like so, and like so. Okay, so we're given a velocity time graph that looks something like this, and I want to break it up into 3 parts. Okay, so this is going to be part 1, this is going to be part 2, and the rest will be part 3. Okay, all right. Now, if we see here, I'm going to write this equation up here. Displacement is velocity times the change in time. We see that our y-axis and our x-axis are multiplied. Now, when you are multiplying your x and your y-axis, what you're looking for is this thing called the area under the curve. Okay, and I always represent area under the curve as AUC, area under the curve. Now, don't let the word curve trick you. Curve can be a straight line. It could also be something that is curvy. But the important thing is that we want to know what area represents. So whenever you're multiplying your x and your y-axis, okay, what you're looking for is the area under the curve. And for a velocity time graph, your area under the curve is your displacement. So this is what this means. If we were to find the area under the curve for section 1, so this is part 1, I have to first locate my curve. So you see this line here, my function, that is my function curve. So what you're going to do is you're going to find the area from that function down to the 0x axis. Okay, so down to that 0. And so we get here the area of a triangle. And so whatever the area for this triangle is, okay, and we know that the area is 1/2 base times height, that will give us your displacement. So the value for the area of this portion will tell us how far, or the displacement of the object. And for here, we can say the displacement is 1/2 base, which is time, times height. So velocity, 1/2 times time versus velocity. All right, now let's take a look over here. Here we have a different area under the curve. So here, this shape is given to us by a rectangle for part 2. And so for part 2, that rectangle, whatever this area is, will give us our displacement. And for this one, because it's a rectangle, not a triangle, you could just do base times height. So base is time times your height, which is velocity. And you can get those values by looking at, like this will be your time, right? How big that time is, and your height is whatever your velocity value is. Okay. All right. Now, part 3 is very unique. So part 3 has the curve going below the x-axis. So in order to find the displacement below the x-axis, you have to do something very unique and special. So the first thing is that we know how to find this area above the x-axis. Okay, that'll just be this triangle. So whatever the area is for that triangle, that will give you the displacement for this time portion. And when you go below the x-axis, remember, you're always going to go from the function, the curve, to the 0. Okay, and so you're going to find the area of this triangle right here. Now, here's what's unique. The area above here, this will give you a positive displacement, and this right here will give you a negative displacement. And so in order to find the total displacement for part 3, you have to add this positive to this negative displacement to find the total displacement. All right, wonderful. So to do one last example here, we have a acceleration time being multiplied. So if you're given a graph that has both acceleration and time, like so, okay, and let's say you're given a curve that looks like this. All right, we know that when you're multiplying the x and the y axes together, the area under the curve will give you, for acceleration time, will give you the velocity, because we know base times height. So height is time, base is a, A times t gives you v. So the area under the curve will be our total change in velocity. Okay. All right. Now I wanted to show you this shape because it's one of the most common shapes that you'll see. This is a trapezoid, and just in case you don't know the formula for the area under the for the area for a trapezoid, this is what I like to do. I like to break this shape up into two parts. Okay, this is part 1, that's my rectangle, so this is just base times height, and this is part 2. This is my triangle, which is 1/2 base times height. Okay, so you just got to find the area of this triangle and this area for this rectangle here. Now, just be careful. The bases shouldn't be a problem, but the height for the triangle, okay, you got to find it from whatever this value is up. So this right there. Okay, and then after you find it, you can say that the area total is equal to the area of 1 plus the area of 2. And that'll give you the total area under the curve. And then for this graph, that'll give you the area under the curve, which is velocity. All right, now you can use this strategy for any equation that we come across with physics. And if you're given the x and the y axis, and you're given the equation, and you just got to ask yourself, am I multiplying or am I dividing? Okay, if I'm dividing, you're looking for slope. If you are multiplying, you're looking for area under the curve. Now we started off with the motion equations, but as we move forward, we will use this strategy time and time again. Okay, I'll see you next time. Bye-bye.